Now we introduce our 3 properties of logs. This is big, but you're going to be like, wait a second, this actually rings a bell to me. So let me show you the rule, and I'm just going to write log for all of mine, but it's understood when you write log alone that it's equal to log base 10. So just to save ourselves the writing of the base 10, I'm just going to write log, and these properties work for any base of logs. The first property says the log of x times y is equal to the log of x plus the log of y. So basically what it says is that multiplication turns into addition. You ever heard that before? Multiplication turns into addition. When does that happen? Yeah, it happens with our exponents, right? That's our exponent property. How about this one? The log of x divided by y is equal to the log of x. I bet you could guess it. All right, minus the log of y. So this rule basically says that division turns into subtraction. Ever heard that before? Last one is the power property, is the log of x to a power is equal to, that p comes down in front, p times log x. Or powers turn into multiplication. Another of our exponent rules. So these main 3 rules of logs really just echo the main 3 rules of exponents. So first we're going to just get used to the rules here by rewriting, or sometimes we call these problems expand. Expand. So the log base 3 of x times y is going to expand to the log base 3 of x plus the log base 3 of y. And now I have to have that baby 3 there, right? It's a log base 3, not log base 10. What about number 2? Log base 3 of x over y equals log base 3 of x minus log base 3 of y. In number 3, the power is going to come down in front, 2 times log base 3 of y. And then number 4 is like the grand finale. It puts it all together. It's going to expand to 2 log base 3x plus 3 log base 3y minus log base 3 of z. So kind of putting it all together. That's expanding logarithms. Then we do the reverse where we condense. Then it's like the reverse of this where we rewrite it as what we call a single log. So log base 5a plus log base 5 of b is the log base 5 of a times b. Log base 5 2x minus log base 5 3y is the log base 5 of 2x over 3y. Numbers in front become powers. Subtraction becomes division, x squared over y cubed. And then here that becomes a power, so it could be x to the 1/2, or since 1/2 is square root, you could write it like that. All right, cool. So now these are outdated problems. Like right off the bat, this is an outdated problem because you can do all these on your calculator now, and we'll show you how in class, log change base, or log base. But here, this is like the old-fashioned way of doing it, but it's still a good problem because it reinforces the rules of logs. The log base 3 of 3 is 1 because 3 to the first is 3. The log base 3 of 9 is 2 because 3 squared is 9. Log base 3 of 15, before calculators, we didn't know. But we could rewrite this as the log base 3 of 5 times 3. And that could be expanded to the log base 3 of 5 plus the log base 3 of 3. The log base 3 of 5 is given to me, I'm just going to squeeze that in there, 1.465 in the directions. The log base 3 of 3, I figured out already, was 1, and I add those up, 2.465. The next one, log base 3 of 45, can be written as the log base 3 of 5 times 9, which can be expanded, log base 3 of 5 plus log base 3 of 9. The log base 3 of 5 from the directions is 1.465. The log base 3 of 9 is 2 because 3 squared is 9, so 3.465. So next one is division, right? And what's division turn into? Log base 3 of 5 minus log base 3 of 3. And you end up being like, I don't even need to show my work on this. Like, I can do this all in my head, but it's never a good idea, right? Always show your work. There we subtract. Here, log base 3, 3 minus log base 3, 5. So it's the reverse. 1 minus 1.465. So negative 0.465. Log base 3 of 9 minus 15. The nice thing here is you can take answers that we've already done. So we know that 3 squared is 9. So it's 2, and then we already did log base 3 of 15, 2.465, so another negative 0.465. Which, by the way, that should make sense. Why? 9/15, when I reduce it, is 3/5. So basically the same problem. And then don't be, you can still come up like an answer you kind of know by heart, like 3 to the 4th is 81, so that's just 4. Okay, last thing, application. So rules of logs to solve each equation. What we're going to do is condense one side to a single log. So log 72 over log 9 is the log base 12 of 72 over 9. Since it's both log base 12, I can now set these equal to each other. 72 over 9 is 8, 8 equals 4m, m is 2. You can always check it, but it's going to work. Here, this is going to come up, so this is going to be the log base 5 of x to the 4th over 4 equals the log base 5 of 4. So x to the 4th over 4 is 4, so x to the 4th is 16, and I have to be a little careful. I'm only going to choose 2, not negative 2, even though negative 2 to the 4th is 16. And the reason is you always have to take the log of a positive number, so x could not be negative 2. You might think that the last two are different, or are the same, but they're actually a little bit different. When I condense this, I get y squared minus 16 equals 2. Notice that it is not a log on the other side. It is a number. So we have to loop this one. So we get 3 squared, or 9, equals y squared minus 16. And again, when we square root it, we're only going to do 5 because you have to take the log of a positive number, and negative 5 plus 4 or negative 5 minus 4 would not be positive. Last one, when we condense these, log base 10, y squared plus 21y, just distributed that, equals 2. It's what I call a log-log number, where we have to log loop it. So y squared plus 21y is going to equal 10 squared, or 100. So I got to move that over, squeezing it in here, factoring y plus 25, y minus 4. I get 2 answers, but the only one that works is the 4. Not because the 25 is negative, but because you can't take the log of a negative. And if I were to plug in negative 25, I would be taking the log of a negative. So you get more practice on these on the homework, are properties of logs.